Every atom in your body emits a unique signature of light, determined by the eigenvalues of an infinite dimensional operator. This spectral fingerprint is the key to understanding how functional analysis describes the fundamental building blocks of our universe. In finite dimensions, the spectral theorem allows every symmetric matrix to be represented in a purely diagonal form through an orthonormal basis. This decomposition separates the operator into independent scaling factors along perpendicular axes of the vector space. Hilbert spaces extend this logic to infinite dimensions by replacing finite vectors with functions. These spaces must be complete, meaning every sequence that looks like it is converging must actually find a limit within the space itself.
The inner product provides the geometric structure of a Hilbert space, defining lengths and angles between functions. It allows us to speak of orthogonality and projections in a way that mirrors our three-dimensional intuition in infinite dimensions. Bounded operators are the linear maps that preserve the topological structure of the space. They map finite inputs to finite outputs, characterized by a specific norm that represents the maximum possible scaling factor the operator can apply. For every bounded operator T, there exists a unique adjoint operator, T star. This relationship is defined by the inner product, where the effect of T on one vector equals the effect of T star on the other.
Self-adjoint operators are those equal to their own adjoints. In the mathematical language of quantum mechanics, these operators represent physical observables like position or energy, as their mathematical structure guarantees that measurement outcomes are always real numbers. Unitary operators are the infinite dimensional version of rotations. They are surjective isometries that preserve the inner product, meaning they change the representation of the data without distorting the underlying geometry or losing any information in the process. The resolvent set of an operator consists of all complex numbers lambda for which the operator minus lambda times the identity is invertible. This set is always open in the complex plane, providing a stable region for calculations. The spectrum is the complement of the resolvent set. It is the set of values where the operator fails to be invertible, generalizing the finite set of eigenvalues to include much more complex structures in infinite dimensions. The point spectrum consists of all lambda values where an actual eigenvector exists. These are the solutions to the classic eigenvalue equation, where the operator simply scales a non-zero vector by the factor lambda. In infinite dimensions, the continuous spectrum appears when the operator minus lambda identity is injective but not surjective. The range is dense in the space, but no true eigenvectors exist, representing a fundamental shift from matrix algebra. The residual spectrum occurs when the range of the shifted operator is not even dense in the Hilbert space. For self-adjoint operators, the residual spectrum is always empty, which simplifies their analysis and physical interpretation significantly. Compact operators are the closest infinite dimensional analogs to finite matrices. They map the unit ball into a set with a compact closure, ensuring that their behavior can be closely approximated by finite dimensional systems. Every compact operator on a Hilbert space is the limit of a sequence of operators with finite rank. This allows us to use standard matrix techniques to study complex systems by projecting them onto manageable finite dimensional subspaces.
For compact operators, the Fredholm alternative dictates that the operator behaves nearly identically to a matrix. Either a unique solution exists for all inputs, or there exists a non-trivial kernel of eigenvectors for that specific value. The spectral theorem for compact self-adjoint operators provides an orthonormal basis of eigenvectors. The operator can be written as an infinite sum of projections, where each projection is scaled by its corresponding real eigenvalue. A crucial feature of compact operators is that their eigenvalues must accumulate only at zero. This means that high-frequency modes or complex interactions eventually become negligible, allowing for stable numerical simulations and truncated models.
Each non-zero eigenvalue of a complex operator has only a finite multiplicity. This ensures that every individual energy level or resonance mode corresponds to a finite dimensional subspace, preventing infinite energy densities in physical models. When an operator is bounded but not compact, the discrete sum of eigenvectors is no longer sufficient. We must transition from discrete arithmetic to the calculus of measures to describe the full range of the operator's action. Consider the operator that multiplies a function by its independent variable. This operator has a purely continuous spectrum and no eigenvectors at all, yet it is a fundamental component of the position operator in quantum physics. Because no function in L2 can satisfy the eigenvalue equation for the multiplication operator, we cannot find a basis of eigenvectors. This necessitates a more generalized approach known as the resolution of the identity. A resolution of the identity is a projection-valued measure that assigns a projection operator to every Borel subset of the real line. It essentially slices the Hilbert space into infinitesimal pieces according to the spectrum of the operator. These measures satisfy the properties of standard probability measures, but return operators instead of numbers. Summing these projections over the entire real line always results in the identity operator, ensuring the entire space is accounted for. The spectral theorem states that every bounded self-adjoint operator can be represented as an integral of the variable lambda with respect to its spectral measure. This is the ultimate generalization of the diagonal matrix form. This representation allows us to decompose any bounded self-adjoint operator into its spectral parts. It provides a rigorous way to analyze systems with continuous frequency distributions, such as the thermal noise in electronic circuits. The convergence of the spectral integral occurs in the strong operator topology. This means that for any specific vector in the Hilbert space, the sequence of finite approximations will converge to the correct transformed vector. With the spectral theorem, we gain the Borel functional calculus. This allows us to apply any Borel measurable function to a self-adjoint operator by simply integrating that function against the operator's unique spectral measure. We can now rigorously define the square root of a positive operator. If the spectrum of a self-adjoint operator is non-negative, the functional calculus provides a unique positive square root that commutes with the original operator. Commuting self-adjoint operators share a common resolution of the identity. This mathematical fact allows for simultaneous diagonalization, meaning we can find a representation where both operators act as simple multiplication by their respective spectral values. Many critical operators in physics, like momentum and position, are unbounded. They cannot be defined on the whole Hilbert space without violating the requirements of continuity, necessitating the study of domains and closed operators. An unbounded operator must be defined on a dense domain to have a well-defined adjoint. This ensures that we can still perform geometric calculations even when the operator scales certain vectors to infinite lengths. Closed operators have a graph that is a closed subspace of the product space. This property acts as a substitute for continuity, allowing us to utilize the powerful tools of the closed graph theorem and spectral theory. In infinite dimensions, symmetry is not enough for the spectral theorem. Self-adjointness requires the operator and its adjoint to have exactly the same domain, a technical distinction that is vital for the stability of quantum mechanics. When a symmetric operator is not self-adjoint, we use deficiency indices to determine if it can be extended. These indices count the dimensions of the subspaces where the adjoint fails to match the original operator. The position operator x and the momentum operator p are the canonical examples of unbounded self-adjoint operators. Their failure to commute is not a flaw, but the mathematical source of the Heisenberg uncertainty principle. The uncertainty principle arises directly from the fact that no state can be an eigenvector for both position and momentum. The spectral measures of these non-commuting operators cannot be localized simultaneously in the Hilbert space geometry. Stone's theorem establishes a one-to-one correspondence between self-adjoint operators and strongly continuous one-parameter groups of unitary operators. This provides the rigorous foundation for time evolution in any isolated quantum system.
The Hamiltonian operator is the generator of time shifts. By applying the functional calculus to the Hamiltonian, we solve the Schrödinger equation, describing how wave functions oscillate and spread through the Hilbert space over time. The Fourier transform is a unitary operator that provides the spectral representation for the differentiation operator. It diagonalizes calculus by transforming differential equations into simple algebraic multiplication in the frequency domain. In engineering, the spectral theorem justifies the decomposition of signals into frequency components. This allows for noise filtration, data compression, and the clear transmission of information across infinite-dimensional communication channels. Infinite diagonalization through spectral theory remains the primary bridge between abstract mathematics and physical reality. It provides the rigorous language for energy levels, signal frequencies, and the very structure of the quantum world we inhabit.